Hello. So in this video, I will be explaining the Ghulam Kibriya sir's first assignment, which was on explaining how the shield uh, stops the heat transfer, or actually reduces the heat transfer. So before going into that, I will be explaining the radiation model in ANSYS with a very brief discussion, and I will be explaining a very specific model for radiation. There are actually two radiation models. One is surface to surface, and other is OB. So I am going for only surface to surface, which is also called S to S. So in this model, let's say we have a cell K right here. I have marked it in yellow. So if energy comes into this cell, so the total energy that comes to this cell, let's take it as 1. And as we know, if a body, or let's say surface, gains energy, it will, in radiation terms, will emit the energy, will absorb the energy, and some energy will be reflected. So the absorptivity is denoted by alpha k, the reflectivity is denoted by rho k, and the transmittivity is reflected by this tau k. So this whole aftermath should be equal to the initial incident energy. So thus alpha k plus rho k plus tau k is equal to 1. So this is our first equation. But if we take the surface as opaque, then this surface will not transmit any type of energy from this surface. Thus the transmittivity is 0, and thus alpha k plus rho k is equals to 1. And now this is the equation 2. Again, we know from according to Kirchhoff's law, we have alpha k is equals to eta k. What does it mean? That a black body, if it the energy it absorbs, the equal energy it emits through the body. Thus the absorptivity k is equal to the emissivity k, and we can replace the absorptivity here with the emissivity k here. So thus emissivity k plus rho k is equal to 1, and this is our equation 3. And from the energy balance equation, if this cell, we have to determine how much energy is going out of this cell, we have to, let's say, qk out. I have denoted it with small q as per heat transfer per area. So heat transfer per area is qk, small qk out, and it should be equal to the emissive energy plus radiative energy. So the emissive energy is written in this term, and the radiative energy is written in this term. So anyhow, and now from the Kirchhoff's law, we can replace this reflectivity with 1 minus eta k from the equation 3, and we get our equation 5. So keep this equation here, and let's move on to our next condition. Now if we look at this picture, we can understand that if we focus on a particular surface k, it will get heat from many multiple surfaces that is above it. Let's say the surfaces are j is equal to 1, j is equal to 2, and similarly j is equal to n numbers of cells. So the k will get the heat from n number of this type of cells. So from j is equals to 1 to 3 to n cells to from these cells to cell k, the net heat input that k will gain should be the view factor into the heat going out of each of this cell. And what is this view factor? The view factor is basically how much, if we, let's say we have an eye in this k section, if in this k surface, and this eye, if it sees the j completely, the view factor would be 1. If it sees the j surface partially, then the view factor will be less than 1. So basically the view factor is how much you can see the surface, see the other surface when your eyes is on the k surface. So thus how much heat will be coming out of this surface will depend will depend on the view factor that will come into this K surface. So for that, so for each surface, it will, for each surface, if it has a view factor of jk, so the summation of all of this surface and multiplied by the view factor would be the total heat gain in this surface. So anyhow, we can write the total heat gain in this term, area into heat gain per area. So the if you remember, I just said that small q is heat transfer per area. So area into q should be the net heat transfer. So that input in this K surface should be equal to this value, and we also are dividing this heat surface into area into heat transfer per area, and this will give our equation 7. And now from reciprocity rule we know that AjFjk is equals to Ak and Fkj. So we will replace this term to this term here, and we see that this area and this area gets cancels out. So this Ak and Ak cancels out. So we are left out with Kq in is equals to this summation Fkj Qj out. So now what we have determined is that how much this surface will gain heat per area in terms of other surfaces output heat, which is Qj out. So we will put this value into this equation in here, Qk in and Qk in. So if we put 8 into the equation 5, we will get this equation, and this is our final equation that is transferred into a matrix form to solve in iterative way or any direct method. So if we rearrange this equation even a small bit, I am just putting this part, this term into that side and keeping this side, keeping this term here. And if you look closely at this matrix formation, you will understand this matrix formation represents this equation, and you can and say solve this matrix with iterative methods like Jacobi iteration method or any other direct method to solve for a different type of T1s, and that's how we can get T1 if we want to know the temperature, or Q1 if we want to know the heat transfer per area for a specific surface. So this is a very simplified and brief discussion of the solution procedure in ANSYS for radiation heat transfer models. So now we will start the actual analysis in the workbench. So I'm cutting it here. Let's go to the ANSYS workbench. Okay. So this is our interface for ANSYS workbench, and I will be creating the geometry now. I will be creating the geometry separately, not through this steady state thermal procedure directly. If you see here, if I drag the steady state thermal directly, you can see the geometry. I can create geometry in this workflow, but I will not be able to use this geometry for later purposes. So I will be creating the geometry separately, and then I will start the steady state thermal procedure. So I will be deleting this, and let's thus make the geometry separately. Go to design modeler, and the design modeler is starting. We can see the prompt, and it is the interface for the design modeler. Now we will be creating 3 shields, right? 3 shields. So for the 3 shield, my bad, not 3 shield, 2 surface and 1 shield. So you can choose any one of the plane. I am choosing for the XY plane and going for a look at. I am not being able to touch that though. Anyhow, go for sketching mode, and I'm manually doing it, but you can just click here and the look at button, and you can get a 90-degree view of this plane. Anyhow, let's create a rectangle, a thin rectangle, like so, and let's give it dimensions. Let's give this the dimension of, let's say, 10 meters. mm, and let me first give it a constraint for symmetry along this axis. To bring a symmetry, you have to choose the axis that you want to make the symmetry about. So while pressing the control keyboard, select the symmetry axis and the sides that you want to be the symmetry. I want this side and this side, my bad, uh, this side, and okay, I have selected it wrongly. Let me do it again. So go to draw and then again constraint, and it will be rearrange the symmetry option. So go for symmetry, select this surface, I mean side, and this side. Okay, so the previous one is making the problem. No worry, just go undo and it will undo. Alright, now before going any further, just give the dimension of 10 meter and go for symmetry and make it, tap it carefully actually. So select this surface, this side, and this side, and it will make a symmetry properly. And let's say we give it further dimensions, and I want to make it very thin surface. So I'll give it, let's say, um, 0.01. That will make it very thin, right? And let's bring it close to this to this axis. So select this axis and select any of the point here. Okay, I'll carefully select the points, right click, selection filter, point, and this point. And give this value of h3 0.25, so it's very close to the surface. Let's extrude it and apply the geometries of sketch 1, and let's give it a width of, let's say, 2 meters and generate. So this is our surface. If we watch it closely, let me zoom it a bit. So this is the surface 1, and now we will be mirroring this surface along this axis and at this side. So go for create, body transformation, mirror plane should be the YZ plane, as you can see here. So mirror is the YZ plane, apply, and bodies has to be this body, and apply. And you should have the preserved body too, yes, and generate, and it will create two planes, two infinitely long plane. I am saying infinitely because it is very long compared to the thickness of the plate. And similarly create another surface at the middle of these two plates, which will act as a shield. So let's do that. Similarly go for the XY plane, and let's say make another sketch, go tap on sketch 2 and go for sketching, and similarly draw a rectangle. mm, or maybe I should sketch on this plane, so forget this, delete this, and go for the YZ plane. That would be easier. So go for the YZ plane and go for new sketch and go for sketching, make a rectangle, just closely try to mimic this, and it should be okay. And now let's give the dimensions. This should be 2 meters, exactly how much we extruded, and let's say this length should be 10 meters, and this plane should be symmetric about this axis. So from concept, or from create, go for my bad, not there, just go in the constraints, and from symmetry choose this axis first, and while clicking your control key, select this side and carefully this side, and it should be applied the symmetry. And our geometry is almost done. Then last thing to do the extrude for the shield. The sketch 3 will be automatically applied, and let's give it an extrude of, let's say, 0.01 and generate. And these are the three surface that I will be needing for the analysis. So initially what I will do is make before doing that, before let's say we are going to make one part from three of these bodies. Now you are seeing the 3 bodies. This 3 body problem, there is a problem with the 3 body, because this 3 body are not connected. If I do a mesh for only one body, the similar mesh will not be done on the other 2 bodies. So but if I make one part from all of these 3 body, the same mesh will be applied on all the bodies. So for that, select all of this while clicking the control keyboard and form new part. And now if I give a different type of mesh at this body, similar type of mesh will be applied on the other bodies if I don't give a specific mesh on the other bodies. So our work in the geometry is almost done, but finally I am just making this body suppress. Also suppress this sketch, but sketch doesn't matter, because I want to make the heat transfer analysis without the shield first. So thus I am suppressing the body. Now let's go to the workbench and drag the steady state thermal in this geometry and go for modeling. So now we will be starting the modeling here. So this is the interface for the ANSYS Mechanical. So firstly we will be doing the mesh. So right click on the mesh, insert. Well, we do not need to insert any method here, so just go for mesh and go for sizing and change this adaptive size to no. Keeping this adaptive size, that ANSYS will deliberately choose circle, triangle, or any shape they want to create the mesh, so I will be not be selecting that. And let's give it a proper mesh size of say 0.5, and let's generate, or let's say the thickness is 0.5, so I shouldn't be giving that. Let's say 0.1, and then go for the mesh and generate. Okay, so this is the good enough mesh. The mesh has been generated. So now we will be moving on to the boundary conditions. So right click on the steady state thermal and insert. So what is the right click on the steady state thermal and insert, and firstly the temperature. So initially, alright, I may haven't given it the name selections. So before solving these things, let's give it the name selections in the design modeler part. So come to the design modeler and give the name selection to this whole body. Select the whole body, this name selection, surface 1, generate, select this body, name selection, surface 2, generate, and select unsuppress this and select this body, give it a name selection of, let's say, shield, and generate, and again suppress this and go to the workbench and update, and let's go to the modeling again, and you should see the name selection part here, surface 1, surface 2. Anyhow, so let's give the temperature first. So the surface 1 is this surface, so let's give the temperature to this surface, this side, and apply, and give it a temperature of 800 Kelvin. It was mentioned in the assignment PDF. So 800 Kelvin in Celsius is 527 degrees Celsius. And similarly, right click on this and insert temperature to the second surface, select this face and apply. The temperature here was 500 Kelvin, which is 227 degrees Celsius. And now we will be inserting the radiation condition in the inner surface of the first surface 1 and apply. Okay, I'm putting the radiation in the right surface. Now this radiation surface will be correlation to the surface to surface model, and let's give it an emissivity of 0.2. It was mentioned in the assignment again, and the ambient temperature is 22, enclosure is 1, and enclosure type is open. So all is okay. And now similarly, right click, radiation, now choose this inner face and apply. Also this too, I want to change this to surface, and the emissivity is 0.2 mentioned in the assignment, enclosure 1, type open. And I guess the conditions is done. Now let's create some probes. So go for right click on the solution, insert thermal and total heat flux, and solve for it. Let's look at our heat flux. It's looking nice, I guess. Now generate the animation. So we can see the maximum heat flux is 4336.6 watt per meter square, and the minimum is 0.28034 watt per meter square. So now let's save this animation, as we are to give a presentation on this, so we can add the videos in the presentations or add the animations. If we want to slow down the animation, just make it 4 seconds and it will slow down a bit. Okay, alright, so you can save it now. To save it, stop the animation and go for export option and choose a different file. Let's make a new folder and select this, and let's say transfer without shield and save. Alright, the radiation has been saved. Radiation animation has been saved. So this is the radiation without the shield. Now let's unsuppress the shield body and to the next part, go here in the design modeler and unsuppress this body, and after that go to the workbench and update this model. Update. Now by default the material in these plates has been assigned as structural steel. I can show it to you. If I go in the geometry part and see the solid, you can see the assignment is to the structural steel, but in our assignment it is mentioned that the shield was aluminium shield. So we will be adding the aluminium in our engineering data, and then we should be assigned the aluminium metal to this shield part. So let's go to the workbench again and go to the engineering data, double click on it, and if I am to add a newer material that is already in the access library, go in the engineering data sources and look for the aluminium. You should find it in the thermal materials, and let's say choose the aluminum. Here's the aluminum, and choose the plus option to keep it in the data. You should see a bookmark that will ensure that this aluminum is added in the engineering data. So go in the project section again, and now go to the modeling and go for, you can see a question mark in solid because I haven't assigned a material in the shield. So go here and left click on it, click here and go for, alright, I have forgotten for update. You can see an update option and update here after you have added the aluminium in engineering data. And now if you go here and you can see the aluminium and go to, and now you also see the tick mark after the solid part. And now let's give the radiation to this surface part as well and this surface part as well. So right click on it, similarly insert radiation, let's say this face, and apply. The correlation is also to surface and the emissivity was set to 0.1 and type open and enclosure 1. Similarly, right click here, insert radiation, this face, and apply. Correlation is to the surface and emissivity is to 0.1 and open and enclosure 1. And if we now to solve the total heat flux, the total heat flux is already in the solution. Now in our assignment we also have to determine the temperature for this shield. So go right click on the solution, insert a thermal probe for only this shield body. So let's select the body option and then select this and apply. So now solve the solution and let's look, wait a bit until it converges. Okay, So if we look at the total heat flux, we can see there is a bit problem here because the maximum heat flux is showing in the shield option, and the maximum heat option is also very much high. Hmm. Let's change it to directional and it should be alright. Now solve. Yeah, so this solves it. See, now the maximum is 4208. Before it was much higher. So the first shield is, if the first surface is giving off the heat, the shield is protecting this shield from getting any heat flux, and most of the heat flux is in the blue range, which is of very less, -4. The negative heat flux also actually correlates to heat outgoing heat flux. That means this surface is now giving off heat. That is better for insulation in this whole compartment. So if I have to choose the directional heat flux for this part, I also have to make the directional heat flux for our no shield condition, because I have selected total heat flux for the no shield condition. So for that I will be saving this part before. Let's zoom it a bit, and let's create a nice view. I wanted to give it a parallel section, but it will not be very meaningful because you cannot see much here. Alright, I guess this is okay. So stop this and save the animation and call it with shield and save. And now I have to give the directional heat flux for the no shield condition as well. So you can do that, just go in the workbench, or no, just go in the design modeler and again suppress this part and update the model. And go to the model again. Now if you are seeing a error here, so just delete the every condition for the shield part and it will be okay. So delete this object, delete this object, and it should be okay, and solve it again. And let's see the animation now. So the solution probe is for directional heat flux, and now run the animation. You can see a much higher heat flux here, 4336, and much lower as well. And you can see much of the surface is getting the heat and going in this cyan color region, which is of 1270.5 watt per meter square. So now save this and just give it a proper orientation that it looks fine. Let's zoom it properly. My bad. Okay, this should be the animation. Okay, the animation should be okay in here. So stop the animation and export it again and call it the without shield and save and go for replace existing file. So you can see a maximum heat transfer rate of 4336, and with the shield. Let's look at the videos again. It was saved in here, new folder. Let's see the animations here. This is the without shield. The highest is 4336 and lowest is minus 262.46. Anyway, we will be comparing the highest one only. The highest without the shield is 4336, and with the shield it is 4208. So a bit of reduction with the shield. So this is what we are ought to show in our presentation, that with the shield the maximum heat transfer is lessened. Alright, we have to solve another thing in the modeling from here, that was the temperature of the third surface. So for that I have to export the unsuppress this body again. I should have been more careful to select the temperature before. Don't worry, just you can do it all the way you want. So update, go for modeling again, assign the materials again, aluminium, and now generate the mesh again, and go for the radiation condition in the shields again. Give this shield, apply, radiation is 0.1 emissivity. Again right click here, insert radiation, this surface, apply, and 0.1 emissivity, and now solve for it. All is done. And let's look at the temperature. It's weird, no? Which body is this? Just delete this temperature and let's make a new one for it. Insert temperature, select this body, apply, and then solve. Okay, weirdly it has the same constant temperature all the way. It should not be like this. Did I miss something here? Temperature 227, this temperature is 527, the radiation emissivity is 0. Oh, my bad, the correlation has to be set to surface, and this is also have to the correlation of surface to surface. And now solve it. You have to be careful with the options. It is very common to make this mistake, so be careful while you do your simulations. And let's look at the temperature field again, and you should see a nice contour plot for the temperature increase. Let's give it a proper cut. Stop the animation first, and okay, it hangs a bit. Oh, come on. Okay, we can see it like this. It's all okay. Now let's see the animation. So this is the shield gaining the heat. and you can see the maximum Celsius maximum temperature it gets is 330.87, and the minimum is 273.96 at these corners. So also save this animation. So stop this and export, call it temperature for shield, save. And this is all done for the first assignment of Golam Kibriya sir. And let's do the simulation properly for the presentation. You should make a presentation containing these three animations I have just saved, this one, this one, and this one. I will show the animations one more time. This is for the with the shield, the maximum is 4208, so this is less than without the shield, it was 4336. And lastly, the temperature gain of the shield is 330.87 degrees Celsius. So with this I end the session here.